Hey guys! Okay, we are starting off on slide 56. We're going to finish up chapter 14 in this video. The end of chapter 14 is pretty straightforward with just what catalysts are. We can also talk about enzymes, we'll get there. We just need to kind of finish up some rate laws and then also talking about a fast step versus a slow step. So we ended today in class on rate laws for elementary reactions. If each reaction is elementary, then we would say that its rate law is based on its molecularity. Now remember, we said that molecularity was, we could label it as unimolecular, we could label it as bimolecular, we could label it as termolecular. And unimolecular just means that it's dependent on the concentration of one thing. Bimolecular means that we have two different reactants that will be colliding with one another. And termolecular is going to mean where we have three different things that are colliding with maybe three of the same things, but three collisions that are happening, so three reactants. Okay, so in this case I have A is going to yield products, so that means my rate law is going to be rate equals K times the concentration of A. We call this a unimolecular process because it's first order. So because this is just to the first power, it's unimolecular. For bimolecular, we know the rate law would be, if I have two different ones, A plus B, then I know that the rate is dependent on the concentration of A and B. So then I would call this a bimolecular reaction because it's dependent on the two of these, it's second order. Okay, so if we're looking at this example, it says, if the following reaction occurs in a single elementary reaction, predict its rate law. Okay, so if I want to do that for this one, then I would say rate equals, okay, times concentration of H2 with the concentration of Br2. So this would be my rate law for H2 plus Br2 yields to HBr. Now, experimentally, we actually don't find this to be the rate law for this reaction. The actual rate law for this reaction is Br2 to the 1/2. But you can't possibly know that because you didn't do this experiment. So we can try to write rate law based on this, but oftentimes, if we do that, we're wrong, because what we find experimentally is something different. So, I know that kind of sucks, but they'll tell you on your AP test that it's fine to write the the elementary reaction rate law based on just this reaction based on the formula, not based on the experiment. Okay, let's look at this one. So this says, consider the following reaction and write the rate law for the reaction. Let's assume that it's a single elementary reaction. That means it doesn't happen in multiple steps. Is a single step mechanism likely for this reaction? So, if I would write my rate law, rate equals, okay, my products are nitrogen monoxide and bromine. So I have concentration of nitrogen monoxide, but there's two of them, so that would be to the second order, and then times my concentration of bromine. So technically, this order of reaction would be 2 with 1, so it's technically a third order reaction. And if something's a third order reaction, then that means that it's termolecular. And then it says, is a single-step mechanism likely for this reaction, and explain. So the reason I wanted to add this question is because termolecular reactions are incredibly rare to happen in one step. So this should probably be happening in 2 or more steps. Probably more like 2, but we'll look, I think, exactly at this example in a few more slides. So termolecular reactions, very rare. So because they're very rare, they typically don't happen in just one single step. They're going to happen in multiple steps. So a single step mechanism for this is not going to happen. Okay, so I think your book does a really good job about an analogy with the rate determining step. A rate determining step, what does that mean? A rate determining step means that this is the step that the reaction rate will depend on. So usually in a reaction you'll have something called a slow step and a fast step. Usually we like the first step to be the slow step, so you'll hear that called slow initial. This is what we would prefer. And then we could have a fast step, and if that's the first one, we just call that fast initial. We'll talk about both. So let's say that we have our our analogies here. So from 1 to 2, ultimately I'm going to have a reaction that's going from 1 to 3. I have a midway point here at 2. So I can think of these as being my reactant. Ultimately I'm trying to get over here to my product. So that's my reaction. And 2 is just going to be my intermediate step. Okay, so right now, if I'm just looking at this top picture, I have a lot of traffic over here by this toll gate, or this toll booth. So because I have a lot of traffic here and very little things coming out of it, then I consider that A would be my rate determining step. That's where it's limiting the amount of reactant that I'm actually getting for that reaction to proceed. So my rate determining step, this would be my slow step here. So I have a lot of traffic over here, and ultimately the rate at which all of this is going to be, all of the traffic will be moving through is based on this toll plaza A. But if I look at B, if I look at this particular analogy with my toll plazas, I have pretty much what's entering in here to toll A is exiting out. But if I look at toll B, I have a lot of traffic right here and not very many cars on the other side. So that means right here between steps 2 and 3, this is going to be my rate determining step. So ultimately I have 2 steps. I can get a car from 1 to this kind of checkpoint intermediate place. So I can go from 1 to 2, and then 2 can go to 3. So the overall reaction is going to be 1 to 3, because step 2 is just my intermediate. So if I'm looking here, and toll A is my rate determining step, I'm going to call this the slow step. But if I look at this one, and toll B is my rate determining step, I'll call this the slow one. So rate determining step is just meaning that this is the part or the reaction specifically for the overall reaction that will determine how fast the rate will go. So toll A is determining how fast that reaction will proceed, but in this one toll B is determining that. Okay, so let's first talk about a slow initial step. And actually, let's say one thing first. The slowest, which is ultimately saying what we just said, but the slowest step in a multi-step reaction, let's not say determines, let's say limits. Yep. Limits the reaction. So the slowest step in a multi-step reaction limits the reaction. If we go back and look at that, here's my rate determining step. I can't get all of these cars through this toll plaza if this is my limiting step. So I'm limited by how many reactants, how many cars I'm going to have moving through the rest of that reaction, or moving through that highway. Okay, let's look at this reaction, for example. I have nitrogen dioxide plus carbon monoxide is going to yield nitrogen monoxide and carbon dioxide. So the rate law is experimentally found to be this. But I have 2 reactants here. I have nitrogen dioxide and I have carbon dioxide. So because this rate does not include carbon monoxide, then it's telling me that this rate of reaction is not going to depend on the carbon monoxide concentration. This then would tell us, since this isn't really present in our rate, and since the rate doesn't depend on this, then that there's going to have to be a multi-step process that's going on with this reaction. So, let's say that you're given those two steps. This is a proposed mechanism for this reaction right here. Let's actually write that reaction. We'll write the reaction down here below. NO2 plus, I think it's carbon monoxide will yield, carbon monoxide plus carbon dioxide. Okay. This is the overall reaction, and these are the steps that were required to get this overall reaction. So in step number 1, I have 2 nitrogen dioxide molecules that are going to collide with one another. When that happens, when they overcome that activation energy, then I'm going to produce NO3 and NO. But in step 2, I have one of the products that was produced in this slow step is going to collide with carbon monoxide to produce nitrogen dioxide and carbon dioxide. Okay, so ultimately, if we take our 2 steps, and let's write the overall reaction based on these 2 steps. So I have 2 NO2 plus NO3 plus carbon monoxide yields NO3 plus NO plus NO2 plus CO2. Let's try to cancel some stuff out. So we have 2 NO2s over here. I have 1 over here. So I can completely cross out this one. And let's get rid of the 2 there. One thing that I have in common on both sides is this NO3. I'm writing this in brackets because remember that this one that I'm writing in brackets is indicating that it's the intermediate. So in this first step, I produced NO3. And because I produced this, it can now become a reactant in the second step, which it does. When that happens, that's how you're going to identify your intermediate. So because NO3 was produced, and now it's present in the next step, then that's going to tell me, okay, that's my intermediate. Ultimately, it will also cancel out of your equation. So NO3 is now also gone. But that's how you're going to determine what the intermediate is. So I'm left with NO2 plus CO makes nitrogen monoxide, carbon dioxide. That's exactly what I have here. So your 2 steps together should lead you to your overall reaction. If it doesn't, then you probably have done something wrong. Now, how do you know if a step is slow or if a step is fast? You don't know because we've determined these experimentally. So you're never going to have to say, you're never going to have to look at step 1 or step 2 and say, this one's slow, this one's fast. Those will just be given to you. So when we say that in step number 1 that this is the slow step, then ultimately what we're saying is I'm producing these things and they're being produced, but in the second step, so I have NO3 that's being produced in the first step. That means in the second step, this NO3 that we've produced in the first step is being consumed almost immediately. So it should make sense too, because an intermediate should cancel out on both sides, and they're very unstable, so we usually don't see an intermediate for a long period of time in a reaction. So it should make sense that if I'm making NO3 here and that's my intermediate, the next step should be fast because I'm consuming all of that NO3. That's what we're trying to say. And then CO is not involved then in this slow step, which is the rate determining step. Carbon monoxide is only in that fast step, meaning we're also probably just consuming a lot of that carbon monoxide then as well. So because of that, then that's why we don't see carbon monoxide in our rate law. Okay, so this says the decomposition of nitrous oxide, which is in, that should be a subscript, sorry, in 2O, is believed to occur in 2 steps. So you're given these two steps, the proposed mechanism right here. We want to write the equation for the overall reaction and then write the rate law for that overall reaction as well. Okay, so just like we did on the last one, let's do the exact same thing on this one. I have on the reactant side 2 N2Os. You should also write your states of matter. I am not, just for time's sake. Plus just O yields 2 N2s and O and O2. Okay, well I don't have anything to cross out here with this, but I do have, I don't know why I wrote that one for that. Sorry guys. I have oxygen here and oxygen here, and I produced oxygen here in this slow step, and I used this oxygen as a reactant in the fast step. So because of that, this tells me this is my intermediate. So ultimately, I know this is what's happening at that transition state, or that's that activated complex that we heard about from the previous slides. So oxygen, since it's the intermediate, will be completely consumed, so I can cross that out. So that means that my actual reaction, so write the equation for the overall reaction, 2 N2O yields 2 N2 plus O2. Okay, well, let's check. 2 oxygens, 4 nitrogens, 4 nitrogens. It's balanced as it should be. Now they're asking me to write the rate law. So if I want to write the rate law, how would I do that? Rate equals K. My reactant is here. N2O. And there's a 2 in front of it, which you may say, okay, well it has to be squared then, because there's a coefficient 2 here, so it has to be to the second order. But that would be wrong. And it's wrong because the slow step is the rate determining step. This fast step is where this N2O is going to be completely consumed. So technically, because this is a fast step, and this is the slow step, and this is the rate determining step, and this only has a coefficient of 1, so will my rate law for the concentration of N2O.
Excuse me, teachers, I need the following students in the office, please. Julia Belova.
Okay,
Daniel
let's say that we have a fast initial
Dana
step.
Saul, Abby Campbell.
If we have a fast
Jesse
initial
up to the
step,
office,
then
please. Thank you.
let's say we have 2 nitrogen monoxide plus bromine is making my 2 NOBR. So the rate law for this one is experimentally said to be K, nitrogen monoxide concentration squared times bromine concentration. This is a termolecular process. We just said that termolecular processes are very rare, so they don't happen in a single step. So this just will not occur all by itself. Something else is going to have to happen. Let's say that this is the proposed step. Step 1 is my fast one, step 2 is my slow one, so this is my rate determining step. But I have this fantastic thing right here. I have my double arrows, so it means that it is a reversible reaction. So that means ultimately a reversible reaction will be a reaction that's in equilibrium. So just as much as nitrogen monoxide is reacting to bromine to make NOBR2, NOBR2 is breaking down to make these two at equal rates, and it's happening very quickly. They're consuming one another as much as possible. And then this would be then my rate determining step. Okay, so the rate of the overall reaction, we just said, depends on the slow step. The rate law for that slow step is this. Rate equals K2 times the concentration of NOBR2 times the concentration of NO. But how can we find this? How do I know what this is? We will finish this in class tomorrow.